In today's tutorial, we're going to be looking at how to create a cubic lens distortion shader within the Unreal Engine 4. If we look in our content browser, you'll notice that I've already created a folder with two separate objects, one being mat_CLD for cubic lens distortion, and the second being a cubic lens distortion checker pattern that's tileable. If we double-click our material to open it, you'll notice that I have a set of comments. The first set of comments is the source for the algorithm that we will be using, and the second set of comments is the actual algorithm. So the first thing that we need to do is we need to start to decipher the different elements of this algorithm, and then convert it to be used in the Unreal Engine 4. The first line of the algorithm that we're going to look at is this top comment, which is R2 equals the image underscore aspect times the image underscore aspect times U plus V times V. One of the important things to remember when looking at equations like this is that whatever is on the left side of the equal sign is going to be the product of the equation on the right. This means if we had an equation such as R2 equals 1 plus 1, then it would look something like this. We have a value of 1, a second value of 1, and then when we add them together, this open node is going to be the result, which this will then equal R2. So let's now begin to create this equation using the Unreal Engine nodes. The first thing that we need to create is the image aspect. Now, since I want to use this in a very specific manner, I'm choosing to use the center of the UV space as my image aspect. So to do this, we're going to create a texture coordinate. Set its value of U tiling to 2 and V tiling to 2, and simply add a value of -1. If we start previewing the node, we'll now see that our UV coordinates are centered. Let's select these three nodes and give them a name. This will be our center. Once we've created the center, the next thing that we need to do is split our R and G channels so that we can modify both the U and V separately. To do this, we'll create a component mask. The next part of the equation is that we need to multiply the image aspect by the image aspect. And we'll do this for both the R and G channels. So let's create a multiply node and multiply it by itself. Another aspect of this shader that we want to take control of is going to be the ability to stretch in both the X and Y axis. So to do this, let's create a multiply node and multiply this by a positive and negative value with a negative switch parameter. Let's create a static switch parameter, and we'll call this negative. Now the reason that we're doing this is because we want to both have a positive and negative value when we're doing our cubic lens distortion. However, it'll be nice to set the positive and negative values without them interfering with each other. So our positive value is going to be the X size positive state. So let's right-click and create a constant. We'll then right-click our constant and convert it to a parameter, and give it the proper name. By default, this will be a value of 1. Let's now create our negative state. And by default, this will be a value of 0.25. This exterior multiply will now represent our U. In the description, let's type U. We'll now replicate this for V. And now we will simply rename our X size end state and P state to Y size end state and P state. Since we have now successfully multiplied the image aspect by the image aspect, and multiplied U times U and V times V, meaning the red channel and the green channel, which we did here, we're now going to add these two outcomes together. Let's create an add node, and I'm going to add my U and V. And now we can right-click and start previewing the node. And you'll notice that we have a nice centered circular gradient. Let's now place this into a comment, and the name of this is going to be the R2 function. This add node output is now the equivalent of the equals to R2. The next thing that we need to do is write the second part of the equation, which is going to be our f function, which equals 1 plus R2 times, and then we have an open parentheses, k plus k cubed times the square root of R2, close parentheses. And here we're going to be using our order of operations. This way, the equation will function properly whenever it's set up and fully completed within the node tree. So the first thing that we need to do is we need to get the square root of R2. Since the output of this add node is equal to R2, let's now right-click and create a square root. And we'll simply plug the add node into the square root. The next part of the equation says that we need to multiply k cubed by the square root of R2, and k cubed is a float value. So what we're going to do is create a multiply node, create a constant, right-click, convert it to a parameter, and we'll call this k cubed. By default, this will be a value of 0. The next part of the equation is to add k to our final outcome of k cubed multiplied by the square root of R2. Let's now create an add node and a constant. Once again, we'll convert this to a parameter, and this will be k. Now, since this parameter is going to be important in both creating a negative and positive value within our cubic lens distortion, we will add the negative static switch parameter node and create a k end state and k positive state. So let's select one of our negative parameters, Control C, Control V, and we'll rename this to k underscore end state. Simply create a duplicate, and this will be our P state. For the end state, we want a value of -1. And for the positive state, we want a value of 0.3. These values are also not fixed values, and they can be modified at any point in time to give you a different kind of effect. So now let's plug our P state into false, and our end state into true, and then our final outcome into the B input of our add node. The next part of the equation is to multiply R2 by the final outcome of what's in the parentheses. And remember, this add node is R2, and we can better specify that by going into our description and typing in R2 product. So we'll simply create a multiply node, and we'll multiply this by our R2 product. And last but not least, we need to then add a value of 1. Since this is the end of the equation, we now need to refer this to the function f. Let's select all of our nodes, click C to create a comment, and we'll call this f function. And the outcome of our add node is going to be our f product. Now the last part of our written algorithm that we're going to be installing into the shader is going to be a combination of multiplying certain variables in the already existing equation by other variables and then appending those together. So let's take a look at this. We have our u prime equals f times u, and then our v prime equals f times v. So to create this, we need to go to our f product and create two multiply nodes. The first node is going to be our U prime, and the second is going to be our V prime. We're then going to multiply the F product by U, and we'll do the same with our V prime, except this one is going to be multiplied by V. Now that we've completed the algorithm, we need to do a couple of extra things to make sure that this works inside of the Unreal Engine 4. The first is we need to append these two vectors back together. Since this is U and this is V, then we'll create a append vector and plug the U into the A input and the V into the B input. We'll right-click and start previewing this on the node. Let's go ahead and add a texture element so we can see what's already occurring. We'll go back to our content browser and I'm going to grab this tiling CLD checker texture. And we'll create a new texture sample. If we apply the append to our UVs, we can see what's occurring within our texture. You can see now that we have roughly the right equation, but it's not fully implemented yet. So let's move on to the next part. What we need to do now is correctly blend the UV sets that we've already created. The first thing that we're going to do is create another square root node. We will then plug our R2 product into the square root to get the square root of our R2 product. We'll then create a 1 minus node. I'm going to plug this into the square root, and we're going to create another negative switch parameter. The 1 minus will be plugged into the false input, and the square root will be plugged into the true input. We'll then create a clamp and clamp these values. Let's now right-click and start previewing this node. You'll notice that we've created this circular gradient. To be able to properly modify this, we now need to add a multiplication controller and a power controller. Let's make a duplicate of our negative parameter, create a multiply node, and now create two different float variables that are going to control the circle multiplier. For the P state, we want a value of 0.8. And for the N state, we want a value of 0.5. We'll then plug these into the respective inputs. Let's now create a power node by holding down the E key and left-clicking. This parameter will give us control over the falloff of our circle. For the positive float, we want a value of 1.25. And for the negative, we want a value of 0.5. Now that we've created our proper mask and mask controllers, let's now create a linear interpolation node by holding down the L key and left-clicking. Using the power output node, which is going to be our mask, let's now plug this into our alpha channel. We will then plug our append node into the B input, and we're going to duplicate our center function. And this will be plugged into A. We can now take this final output and plug this into our UVs. You'll now notice with the finished equation that our UVs begin to distort more as they go towards the center of our object. Let's go back to our content browser after we've saved our material and create a new material instance. If we wanted to see the opposite effect, we could go into our static switch parameters and change it to negative. You'll now be able to see that instead of bulging outward, it seems to bulge inward. At any time, you can go into the scalar parameters and modify any of these characteristics to move this around, change the center of the bulge, and how much the bulge is influenced.